Hello everyone and welcome to this video on how to conduct confirmatory factor analysis in the JASP program. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis, structural equation modeling, path analysis, multi-level analysis, and latent class modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources, including statistics workshops that I teach for QuantFish. So in this video here, I want to show you something that I'm really excited about, and that is a way to estimate your confirmatory factor analysis model or structural equation model for free in a software that is extremely user-friendly and that I recently discovered randomly on the internet that I didn't know was capable of doing confirmatory factor analysis and structural equation modeling. And so when I found out, I was really excited about that, and I thought I'd share this with other people who also may not know that the software is really great for running CFA and SEM, especially when you're a beginner and you don't want to mess around with syntax and complicated code. That way you can do everything by point and click, and it works really great. So let's get started and let me show you how this works. So here you can see the opening screen of the JASP software that appears when you open the program. As I said, this is a free open source program that you can download from the internet. Thank you to the folks at the University of Amsterdam who created this and put this online, and it works great not just for confirmatory factor analysis and SEM, but also for a lot of other basic statistics like t-tests, analysis of variance, regression, and others. And it's great as a teaching program too, because it has a lot of didactic features that you can use, graphics, interactive learning tools. It's a great thing to play around with, so take a look at it. Okay, so here I'm going to focus on confirmatory factor analysis. It also works great for SEM, and I'll probably show that in a separate video sometime in the future. So the first great thing I would say about JASP after the fact that it's free is that you can very easily load data into the program, such as an SPSS data file. So all you need to do is click here and then go to open, and you can open recent files that you may have opened already, or you can grab stuff from your computer from some sort of folder or some other database. So there are many options for opening data files, and you can read SPSS data, for example, which is what I'm going to do right now. So I'm going to open this SPSS data file math.sav to show you how we can run a confirmatory factor analysis in this software. And so you can see that here in the point and click menu, you have a very intuitive button that says factor. You can click on that, and then so in that way you could do a principal component analysis, an exploratory factor analysis, or also a confirmatory factor analysis. So let's do that and click on confirmatory factor analysis. And you can see that already you have a results section on the right hand side. Obviously we haven't specified a model yet, but JASP is getting ready to give you some output, so you can already see a chi-square test of model fit table is already being prepared. Right now that table is empty because we haven't specified a model yet. And so on the left hand side we have our variable list, kind of like the same way as it works in SPSS, like point and click. You have your variable list, you select your variables, and then you run the analysis of your choice with the variables that you select. And so here we can get started and specify our first factor. And so my first factor here uses the first three variables in my SPSS data file: KFT verbal, quantitative, and figural. Those are three subscales from a German language cognitive abilities test. And so I'm going to specify a cognitive abilities factor 1 here in my JASP. I can also label this factor. For example, I could call it cognitive instead of factor 1, which is nice. And then you can see already, once I do that, JASP already runs the analysis on that factor. So before I even specify a second factor, already I can take a look at what the single factor model would look like. And you can see the single factor model has a chi-square of 0 because it is a saturated model. When you have a single factor with 3 indicators and the loadings are freely estimated, you have a so-called congeneric model, and then that model is saturated as long as there's only one factor and 3 indicators and you have no other variables in the model. So therefore this chi-square here is 0. But we do get the factor loadings here and standard errors, z-statistics, p-values, confidence intervals. So it's very nice. You get all the information in a table that already looks like an APA style table. So much nicer than other programs. And now, of course, this may not be what we want because we're not interested maybe in the single factor saturated model. So let's go ahead and specify a second factor here before we take a closer look at the output. And so you do that by clicking on the plus button here. So it's very intuitive. So that way I can include a second factor. And now I'm going to call this factor math. So I'm going to add some variables that are related to a math test for my second factor. Those four variables, math 1 through math 4. I'm going to use these for my math factor. And you can see automatically the output on the right-hand side gets adjusted. So now there's a second factor. Now the model is no longer saturated because we have a lot more covariances and there are now restrictions in the model so that the covariance structure is not fully perfectly reproduced by our model. But you can see that the chi-square value here, even though it's not 0, it is not statistically significant. So you can see the p-value is 0.075, which is not significant at the 0.05 level. So this model fits the data well. It does not have to be rejected according to the chi-square, which is indicated by the fact that the chi-square is not significant. So that's nice. You also get a baseline model chi-square, which is for a model that assumes that all covariances between all those 7 variables are 0 in the population. So it's an independence model or 0 correlation model. And that chi-square, of course, looks terrible because that's an unrealistic assumption. We have significant correlations here in our data. And so a null model that assumes 0 covariances is not acceptable. That chi-square would be highly significant, even though JASP here does not give the p-value, but rest assured that a chi-square of 1257 with 21 degrees of freedom is highly statistically significant. So our model fits well. The independence model does not fit well as expected. And so we can take a look at the parameter estimates. You can see that now we have loadings here for both our first factor, the cognitive abilities factor, and we have the loadings for the math factor. And of importance, those loadings are unstandardized. That's why they are so large, or that's why they can be so large. Standardized loadings in a factor model like this would not be larger than 1 unless you had a Haywood case or you had a specific factor model with cross loadings and correlated factors. But typically the standardized loadings in a simple structure CFA should be between -1 and +1. And so this shows you these are the unstandardized loadings with their standard errors, z-statistics, p-values, and also confidence intervals, which is very nice that all that is given here in this very intuitive, pretty looking table. The factor variances by default here are standardized to 1. So this is the standardization option or the identification option that JASP uses. So the factor variances in this case are not interesting to look at. They are standardized to 1. The factor covariance is given, which can be interpreted as a correlation because the factor variances are both 1.0. So then the covariance is equal to the correlation, and you can see 0.85 is a strong correlation. So the cognitive ability scores at the latent level are very highly correlated in this sample with the math scores. So there's a very strong positive association between cognitive ability scores and math scores in this sample here. There's also a standard error for the correlation, a z statistic and a p-value, and you can see obviously this very strong correlation is significantly different from 0, so it's a highly significant, strong, positive correlation. There's also a confidence interval for the correlation, which is pretty narrow, so you can see it's between 0.8-ish and 0.9-ish, so it's a pretty good confidence interval, not too wide, which is it's due to the fact that we have a good sample size here. Next are the residual variances. Again, those are unstandardized, and standard errors and so on are also provided for that. So this is what JASP gives you by default in terms of the output. It's the fit statistic, the chi-square, and the unstandardized solution. Now, typically we're interested in more statistics than that. And the nice thing about JASP, again, is that on the left-hand side, you can pick more very easily by point and click. The first option here on the left at the bottom is that you could specify a second order factor. So you could say, oh, I want to test whether those factors that I specified above, those first order factors, whether they measure a second order factor. Now, in this case, it doesn't make a ton of sense unless you think that there's maybe a G factor of cognitive abilities where one facet is a math factor, one factor is a cognitive factor, but typically I would probably not do that, but just to show you how it works, you just highlight the factors that you think are measures of a second order factor. You put them on the right hand side where it says second order factor, and that way JASP will then give you a second order model. So already you can see a new table has been added with these indicators, cognitive and math, and the loadings here, the unstandardized loadings. The model here is identified because all factor variances are constrained to 1, so that way you can identify the model even with just 2 indicators of the second order model. So that way, so say this model would be turned into a second order factor model. And you can see the fit changes a little bit here because of the equality constraint on those standardized, on all those variances, and so that may not be realistic or may not be what we want. So let's get rid of that again. We can just just move these back, and so go back to our first order model, get rid of the second order model, and voila, now you can see we're back to our original first order correlated factors model, which had a better fit. Next, you can click on model options, and you can see that you could include a mean structure, which is a relevant option for some models. For example, when you have a growth model or longitudinal factor model or a multigroup model, in those situations you would want to include a mean structure. Here in this cross-sectional model, it's probably not relevant for us. When you do that, there are different options for how to identify the latent mean structure that you can select from here. You can also specify a model with uncorrelated factors. So you can click this button to test the assumption that factors are uncorrelated. When you do that, then of course we get a horrible chi-square on the right hand side, 264, 14 degrees of freedom. It's highly significant because these factors, as we saw, were very strongly correlated above 0.8. So then assuming that they're uncorrelated is of course not going to work. It's not going to fit well, and the chi-square confirms that uncorrelated factors here cannot be assumed. So let's reverse that. That was a bad decision. And so now we're back to our model with correlated factors. And again, 0.85 was the correlation here. And that's, of course, much different from 0. Now, another thing here is that the model identification default can be changed from fixing factor variances to 1 to using a marker variable. So you could use an approach where you fix one loading instead of fixing the factor variances. And when you select that, you can see again the output here changes. The fit does not change because it's an equivalent model. So you get the same chi-square as before, but you can see now the first factor loading on each factor has been fixed to 1 instead of fixing a factor variance. You can see now the factor variances in the table below the loadings are freely estimated which in some models is preferable. So for example, when you have longitudinal models, longitudinal CFA, you don't want to assume that the factor variances are all equal to 1 typically, because that would imply that factor variances could not change across time if it's the same construct measured on multiple time points. Likewise, when you have a multi-group model, you wouldn't want to assume that all factors have equal variances before testing that appropriately, and so then the marker variable option may be better, or there's another option here that is effects coding that you could also use to identify the model. Next is an option to specify residual covariances, so that would be correlated errors, which you have to be careful with, but adding those post hoc after maybe you find that the model doesn't fit well. It's not generally recommended to just simply try this out and see, okay, which errors could I add to improve my model fit? So that's an option that's maybe a little bit too easy to use, and you should be very, very careful applying residual or error correlations without having a very strong theoretical justification for that. Next is a multi-group CFA option. So you can run the model as a multi-group model by just simply picking a grouping variable in your data set, which in this case here, I don't have one. So, but for example, gender could be one, or country, or something like that. And so then you could just simply select that from the list. You can select from different levels of measurement invariance even. So you can fit a configural invariance model, a metric invariance model with equal loadings, a scalar model with equal loadings and intercepts, a strict invariance model with equal loadings, equal intercepts, and equal error variances. So it's very, very nicely laid out here. Also, you can select additional output, which may be relevant. We may be interested in looking at additional fit statistics, even if it's just to satisfy reviewers. So maybe the reviewers want to see something other than the chi-square. So when you click on additional fit measures, then on the right-hand side, you get a whole bunch of other fit statistics, the CFI, TLI, Bollens indices, the information criteria, AIC, BIC, the RMSEA, and many other fit statistics that you can select from. Also, you can select R-squared, which is useful to see what the individual variable reliabilities are. So this would be for each scale here, for each indicator, the amount of variance or the proportion of variance that is accounted for by the factors. And that's, so say, for individual variable reliability, you can see those aren't great here. For those subscales, the subscales are relatively unreliable. The reliabilities range between 0.427, which is really not good, to 0.65-ish. So that's still not very good. So you can see those scales per se, the indicators alone, are not so good. However, we would typically use them in the aggregate, meaning as a composite. So we would aggregate across the KFT subscales, and we would aggregate across the math subscales. And then we have variables that have, or aggregate or sum score variables that have higher reliabilities, because when you have more items, more measures, then reliability increases. There's more opportunity for errors of measurement to average out. And that's well known from, for example, classical test theory and the Spearman-Brown formula. And so therefore, we typically consider composite reliability indices in addition to those individual reliabilities. And another really great feature about JASP is that they have composite reliability also available. And you get that by clicking here on reliability, which I love that. They don't pay me, by the way, to do this video. So this is purely voluntarily that I'm talking about this here, because I really like it. And so when you take a look at the reliability table at the very bottom, you can see you get coefficient omega. So that's a composite reliability measure for congeneric measures, so for variables that have different loadings, like in our case. You also get coefficient alpha, which is under the assumption of essential tau equivalence. So that would be if the variables had equal loadings on their factor, which in this case they don't. So technically speaking, strictly speaking, Cronbach's alpha here is not appropriate because we are using a congeneric model, not a tau equivalence model with equal loadings, but you can see they're similar. So coefficient omega is a bit higher, 0.788 for the cognitive ability sum score, and for the math factor sum score it would be 0.822 under the assumption of different factor loadings, and those are okay reliabilities, especially for the math factor. That's pretty good. For the cognitive factor it's okay, so almost 0.8. And there's also a total, which doesn't make sense here because that would mean if we aggregated all 7 variables, which we probably wouldn't do because they measure different dimensions. But this is really neat, in my opinion, that you get coefficient omega and coefficient alpha here, which many other programs for structural equation modeling don't offer that. And so that's really nice. You can also take a look at the implied covariance matrix by the model. You can look at the residual covariance matrix. You can look at modification indices to see if your model can be improved. So those are all things that we would also find in standard software for structural equation modeling that can be helpful. And one thing that I also really like is that you can show the corresponding LAVAAN syntax. LAVAAN is the underlying R package that JASP uses to estimate the parameters, fit statistics, and standard errors for the model. And so if you want to learn LAVAAN, you can find the syntax here, which I find that also very nice that they add this feature where you can save your underlying LAVAAN syntax. Next, we can click on plots, and so here you can get, among other things, a model plot, so a path diagram with the parameter estimates. That's something that you might care for. Maybe the standardized parameter estimates you might want to take a look at. It takes a little bit of time for JASP to create that path diagram, and I think it appears at the top. Takes a little while for it to put it together. So let's see if we can find it here. There we go. It's actually at the bottom. And so you can see the model plot with the 2 factors, the factor correlation, the standardized loadings are provided here in the plot, which are around 0.7 for those variables. Let's take a look at advanced, also see what we can get there. And here you can get, you can choose which package you want to mimic in terms of the output. The default is LAVAAN. You could also mimic Mplus or EQS if you're used to that or you want to learn that. And then you can also select whether you want standard asymptotic standard errors for the parameter estimates or whether you want robust standard errors or even bootstrap standard errors. And the default is also that missing data is being handled with full information maximum likelihood, which is another strength, in my opinion, of the program that allows you to handle missing data with ease. FIML is one of the methods of choice for handling missing data under the assumption that the missingness is missing at random. Another option here is listwise deletion or pairwise or two-stage, and so you have a bunch of options there to deal with missing data, which is nice. And you can select from different estimators. The auto estimator's maximum likelihood, which you can also explicitly choose. And then there's GLS, WLS, ULS, and DWLS for categorical variables. The standardization here is none by default, but you can also choose to standardize the latent variables or to standardize all variables. So you can look at a standardized solution as well. So let's take a look at what happens when we do that. I guess that actually does not give us the standardized solution, but I know we can find the standardized solution somewhere other than in the path diagram. So you can find the standardized parameter estimates somewhere. Let's see where they are. Model options. I can't find this right now, but you definitely get them in the path diagram when you select standardized solution right here. And so that way you get, oh, actually they are presented here. I just missed it. So you can see the last column has been added to the table, STD estimates all. So that's the completely standardized solution. So those would be the standardized residual variances. And then also above in the loading table, factor loadings, you can also find the standardized solution at the very end of that table. So it's very comprehensive, it's very intuitive, very easy to use, a great option, especially when you're a beginner in confirmatory factor analysis. Maybe the only downside that I can see right now is that it makes it maybe a little bit too easy for you to specify all kinds of crazy models. So be careful when you use this option, because you may specify something that is not meaningful, that is nonsensical, just simply because it's so easy. So still think about, so say carefully what you're doing here, but if you know what you're doing, then this is a great option to specify a factor model quickly with all kinds of relevant information, and to do that for free, since JASP is a free software program. Thank you so much for joining me today for this video. If you liked it, then please consider subscribing to this channel, and also don't forget to check out the description for additional resources that are in the description below, and I'll see you next time.